All right, let's see. See who we got. Hasn't registered that we're live on Twitch yet. All right, let's see. All right. Awesome. We've even got some chatting. Okay, so to catch everyone up, I had a sort of very annoying cold that my daughter brought from daycare. I'm pretty sure it's not COVID because of a bunch of negative COVID tests, but it is definitely still making me cough up my lungs. So I'll do the best I can, and we'll see how things go. Oh, there's a bad link. Oh, lol. That's funny. Let me fix that link. Silly Twitch. Or silly Discord, I guess. Okay, cool. All right, let's make this happen. So, the reason that we are gathered here today is that basically Baby Shell is not going so hot. I think it was probably the holiday weekend, but if we look at the grades, I mean, I'm not going to show the grades on stream, of course, but if you look at the grades, it's pretty bad news. There's a class average of 30% right now, and about half of the class hasn't solved anything. So that's not optimal. Embryo ASM is going better. There's a class average of 68.9%. That's good. But I mean, that's better. Ideally, you'd have a class average of 100%, right? But we'll get there. So what will probably happen is we'll extend these two until Thursday and then figure out the impact on the schedule later, but haven't made that final call yet. But I wanted to do this stream despite my cough coming back to actually shockingly helps to talk. I've just been basically laying over there playing the Switch in complete agony for a day. But yeah, so I wanted to do office hours specifically on Baby Shell. We'll give it an hour or so to try to get people past that initial complexity. All right. So with that in mind, let me do a very quick run through of Baby Shell level 1 so that we have yet another quick run through for those that missed and haven't caught up with the previous office hours or the previous live event, and then we'll go from there with questions. So just real quick speed run of Baby Shell level. Oh man, why doesn't this work sometimes? That works. Right? Yeah, just this guy doesn't work. All right, one sec. Let me fix this. No, and come on. Yes. Okay, good. We're back in business. OBS, man. All right, cool. So let's dive in here and sorry, I'll try to mute myself for the coughing. That one was a little bit of a surprise. All right, shellcode level 1. Start up in practice mode. Just people have been scraping the flags from the stream and trying to submit them, which is silly because obviously that's not going to work. And that false alarms are cheat detection, although you could consider it a true alarm. But anyways, don't do that. So let's just reset the state here. This is still from last time. All right, baby shell level 1. I can SSH to hacker at dojo.pwn.college. That's not gonna work because it's the wrong key. Where's my key? I guess I haven't set it up yet. Okay, let's set the boom. All right, done. Let's do this. Okay, so now I can SSH in. What the hell? Oh, oops. Yeah, this should be just Dojo. The private key. What the hell? Is it not properly? Oh my God. It's the stupidest issue to have. Maybe I need to restart my, oh, it doesn't make any sense. No. Okay, admin panel, this all works. Let's just redo it. Here's my public key. Is that what's on there? No. I must have screwed something up. Oh, this has new lines in it, maybe, and that's why it's screwed up. Yeah, there's spaces and stuff. Okay. Oh my God. Hold on. Let me install Xclip. We'll just. Wait, is it Xclip board? Yeah. No, what's going on? Sorry, guys. Obviously, I'm not on my. No, this is not good. Okay. All right. Not in tip-top shape. All right, we'll try this. Update. Updated. Server accepted. Okay, good. So it was a copy-paste error, or rather, because Screen does stupid things to my terminal when I catted dojo.pub. Oh, yeah, obviously it's not going to be here. When I catted dojo.pub and I copy-pasted this copied a bunch of new lines, which when I pasted them into here, became spaces, which screwed up pwn college. Okay, awesome. So anyways, it works. Here we are in baby shell level 1. If you run baby shell level 1, it basically just says, hey, we're going to read in your shell code and we're going to run it. End of story. All right, so reading in and running shellcode, no problem. We have shellcode. If we created this flag.s, it's a very simple shellcode that opens the flag, reads the flag from the flag file, which is passed in here, and then writes the flag to standard output, and then cleanly exits. Okay, cool. We had a simple way to compile that into an ELF and extract it, but of course we can also just use pwn tools directly. All right, so here's our flag. I did this on my local machine, but I can SCP it over to the dojo. All right, and then we simply cat flag.bin through challenge/baby shell, and the shellcode gets conveniently disassembled for us, executed, and it gets the flag. All right, so this is level 1 of baby shell. Now let's open it up for questions. Any questions on baby shell? Of course, later levels, what's the complexity? Well, your shellcode needs to pass more and more constraints. So shellcode without null byte, shellcode without certain other characters, shellcode that has to survive a sort. Yeah, a lot of good stuff. Question is, why does move AX hex 3C have null bytes? All right. So let's tackle that one first. We're going to tackle this one in 1 second. We're going to tackle this one in pwn.college or in pwn tools. Set the context. Okay, so now we can do pwn.asm move AX OX 3C. And the question was, of course, why does it have null bytes? And it does have null bytes. Ah, okay. So we can do a very nice thing called dot hex maybe. Yes, there's the only good feature of Python 3 is dot hex on a byte string. All right, so we can hex encode this to see what the hell's going on. So move AX hex 3 encodes to 66 or samples to 66 B8 3C00. All right, 3C is obviously our constant. Here's our 3C. If we do 42, that turns into 42. Okay, cool. What else can we mess around with? Move BX. If we change it to this becomes, instead of B8, becomes BB. That's just a different bit that's set in a bit field representing what register to use. This 66 is probably move. We can actually play around with that by changing it to add. Oh, no, I was wrong. 6683 C03C. Okay, so add works very differently. Let's see what might be. Anyways, if we have questions about this encoding, there is a resource that we can use, and it's linked off of there's people spoiling this on Twitch. All right, it's linked off of pwn.college. If you go to pwn.college modules, shellcode. All right, there are. Oh shit. Well, I should have linked it. Here is an awesome, maybe I linked it off of the embryo ASM one. No, okay, my bad. I will link this. So if you search for coder 64 rather, this is an awesome x86 assembly listing. Am I sure it's not linked? It's got to be linked somewhere. How is this possible? Oh, no. Okay, here we go. x86 64 assembly listing. Okay. Whew, it was linked. So this is a table of instruction encoding in x86. All sorts of different stuff. If you click on this 66 that we have in here, so if you do 1 byte opcode index 66, sorry, here we see 66 is an operand size override prefix. So I guess that's what's telling it to use. No, so here we go, 66. That's what's telling it to use GS. Okay, makes sense. Then if we go back, the next byte is 8.3. So let's go look at 8.3. Or sorry, GS. So the operand size override prefix 66 probably forces it to use the 16-bit long register part. Let's actually try. So here's move AX, here's move AL. Very different. Okay. Move AX, move EAX. Yeah, here's an interesting thing. Move AX 3C is 66B8 3C00. Move EAX, that prefix is gone. It's just B8 3C and then a bunch of zeros because EAX is a 32-bit value, right? That's pretty cool. What about AL? AL is just B0 C3. Okay, anyways. So 8.3 is the actual opcode that we're looking at. If you look at 8.3, click here. 8.3 is add. No, sorry, not 8.3, B8. Sorry, guys. B8 is move. Boom. Move, register, immediate. There's our opcode. Okay, so now we manually are disassembling x86, but the interesting thing, the original question is, why is this 00 here? Well, because AX is a 16-bit register, right? Now, let me bring up the appropriate slides. Appropriate slides are here. And we have this partial register access, and this is for RAX, but here it is for all of them. AX is a 16-bit register that references the lower 16 bits of RAX. AX is broken into AH and AL. When you move something into AX, you're moving a 16-bit value. That 16-bit value is actually implicitly 00C3C. That's where the 0 comes from. Okay? If you had done 01.3C, now it's a 01. Big success. If you really only need the last 8 bits, you want AL, right? Again, AL, AX. All right? AL references the last 8 bits of AX, the last 8 bits of EAX, the last 8 bits of RAX, right? It's that last 8 bits of that register. And it encodes into a nice, B0 3C. And if we look up what that is in the assembly table, B0 3C, so B0 is move 8-bit register immediate. Cool? Cool. All right. Okay. Let's see. Other things on Twitch, people agreeing with me about how much Python screwed up strings. Yeah, Python 3 is a problem with that. Number 3, number 7, and the concept of getting shellcode short enough to do 12 bytes. Let's take a look at number 3 first. All right, we're going to run number 3. Practice mode again. All right, connected. Perfect. All right, so we are live in number 3. What does this challenge do? And of course, please remember in /challenge there is the source code as well. So you can actually read what the thing does, but it'll also tell you what the thing does. All right. So it maps some memory for your shellcode, reads in that into your shellcode, and the challenge requires that your shellcode have no null bytes. All right, let's run through how we would tackle this. So we have my flag.bin that worked for level 1. Let's just try it. All right, boom, fail. We have a null byte at byte 3. In retrospect, we should really disassemble things before we fail you. Let me write a quick message to, let me file a quick issue on Git. Hold on. This will improve people's lives next iteration. You might not care about them that much, but I'm sure you care a little bit. Title, disassemble baby shell code before rejection. All right. Okay. Filed. All right. Anyways, back to reality. We failed to filter at byte 3. So at byte 3 of our shellcode, let's hex dump it and see what the hell's going on. We have a null byte. This is byte 0, byte 1, byte 2, byte 3. Shit. Null byte. Okay. Let's go back here and iterate until we are null byte free. We're going to obj dump our flag.bin. Sorry, flag.elf. Here is our shellcode. We move RSI 0. Well, shit. That's a whole lot of null bytes. So let's start by eliminating that. So let's back this up from flag.s to null.s. Null.s. Okay. So this guy is first on the chopping block. Let's actually build out the rest of our, so instead of flag here, we'll do null. Of course, you should have shell scripts that do all of this, or aliases, because this is extremely error prone, and we will at some point fuck it up and have problems. All right, so this, okay. Obviously, we have null bytes. If you want to be very cool, we can grab this for 0, and it even highlights null bytes for us. Awesome. But of course it, well, I guess all of the shellcode addresses will have null bytes, so that's good. I mean, this isn't obviously part of the content, but this is our shellcode. All right, so we have null bytes all over the place. First things first, move RSI 0. What can we do about this? There are two things. One is we use the same trick that was alluded to with this AL, right? Move AL 0 had no, or move AL something, move AL 1 or whatever had no null bytes, but you know, and there is a way to get at the last 8 bits of RSI. It would be SIL. The problem is we're not trying to set the last 8 bits, we're trying to wipe it out. We're trying to make it all 0. Well, luckily, there is an easy way to do this, right? We can, instead of this, we can do XOR RSI. If you XOR a value with itself, it'll be 0. XOR RSI means XOR RSI with RSI and store the result into RSI. It stores the result into this first value. XOR RSI 10 would be XOR RSI and store with 10 and store the result in RSI. Okay, so XOR RSI will 0 out RSI, and it doesn't have null bytes. All right, next on the list, load effective address. This seems like a tough one. The null bytes here comes from encoding this offset of 45. Let's leave this for later. We can initially let's fix up this stuff, right? So here, move RAX 2. Right. Well, earlier on we were playing around with move AL. It had no null bytes. That's fine. Let's do that instead of move RAX2. Here we'll do a to do here. All right, so move AL2. All right. Boom. No null bytes. But when we move to AL, we might have values still left over in the rest of the register. When we move to EAX or EBX or ECX, that'll zero out or sign extend the rest of the register, and you're mostly good to go. But if you move to AL, it won't touch the rest of the register. Why is that? That is that difference there? It's a historical oddity that AMD put in when they created AMD 64. But we have to live with it. So before we do this, we should zero out the register. And that's easy. XOR RAX RAX. Boom. Still no null bytes. And now this is correct. Okay. So where's the next null byte? Move RDX 64. Of course, why is this problematic? Because we have this 32-bit value. Why is it 32 even though this is RDX? It's just the encoding of the instruction that the assembler chose. It can be a 64-bit value. That's this right here, right? So we could do OX11, 22, 33, 44, 55, 66, 77, 88. And it would be perfectly fine. This just is a very long instruction. But to save bytes, since that value is just 64, the assembler used a 64-bit move. Anyways, we want to move RDX 100. Well, we can use the same strategy here. First, we zero out RDX. And then we move to the lowest 8 bits of RDX, which is DL 100. Okay. Wait. Yeah, correct. Okay. Boom. No null bytes. All right, move RAX 0. Again, XOR RAX RAX takes care of this for us. And then RAX is now 0. All right. Move RDI 1. Same thing here. XOR RDI RDI. Move DIL 1. Be very careful. A very common source of errors is the difference between DIL and DL. DIL is the least significant 8 bits of RDI. DL is the least significant 8 bits of RDX. Don't get those mixed up. You will get them mixed up, but just when things aren't making sense and you are using either DIL or DL, stop and think, are you using the right one properly? All right. So, move DL 100, all is good. Oh, yeah, here. Move DIL 1, all is good. Okay. Boom. So, here we have move RAX 1, same sort of thing here. XOR RAX RAX. Move AL 1. Now, someone mentioned inc. So instead of move AL1, we could just increment RAX, right? So we say, okay, no problem. Increment RAX. Someone on Twitch mentioned inc. Boom. Inc RAX. No null bytes. So you can do either one. This is a little more explicit. All right. Now, two more things here. Move, and then we have to face the final boss, the load effective address. Okay. So move RAX 60. So, sorry, XOR RAX RAX. Move AL 60. XOR RDI RDI. Move DIL 42. Boom. Okay, almost there. So there's a couple of things that are still problematic. One of these things that's not shown here is the null byte at the end of the word /flag. I actually have no idea why PDB doesn't output it, but if I hex dump flag that bin, it's right here. All right. Not flag, but that bin. Null, not bin. This null byte and then these null bytes are problematic. And again, you can highlight them by grepping for it. Cool. All right. This one we can deal with in a second, and the way that we could deal with it is we just don't put a null byte there. There might be memory might be null anyways. It actually probably is. A null byte is the most common value for a byte of memory, so we could just roll the dice and hope. But we could also say flag null. We can put a 1 byte here, right? What happens there if we go boom? Oops, that byte. All right, so we have a 1 byte here, and then of course we can move IP plus flag null or decrement IP plus flag null. Nope. Yeah, ambiguous pointer size byte. Can decrement that byte. All right. So now there's no null byte here, but in our decrement, this decrement, of course, will turn it into a 0. In our decrement, there are null bytes here. And these null bytes are here because of this RIP relative addressing, right? One sec, I have to blow my nose. I'll be right back. All right, I'm back. So, RIP relative addressing tells the CPU, hey, get the value of RIP and add something to that. That something is always going to be a 32-bit value, and so it'll have null bytes in it. There just isn't 16-bit and 8-byte RIP relative addressing, to my knowledge. I'm not a complete 100% guru in this. So if you know something different, let me know. I'd be really interested in that. But as far as I know, you can't do this RIP relative stuff, as in RIP plus something, without encountering null bytes. So this is no good for us. So what do we do now? Well, there's a couple of things we could do. We know the offset of this, right? Because it's something that it depends on the other instructions, etc. But we could figure it out. We could manually build this instruction. We could figure out how to get the instruction pointer, blah, 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 blah. That is a lot of work. A lower amount of work is to build the value for /flag on the stack and just use that to refer to the flag instead of this ASCII string in our shellcode. So let's remove that. Let's remove this. And here we're going to build in so that RDI will point to the string /flag. How can we do this? There are two ways. One way is we can, and that way I think is in the slides actually. Let me. Oh shit! Nope. All right. If we go common challenges. All right. One way to build up /flag is to put it into basically EBX here. So we move the value flag into EBX. We shift RBX left by 8, and then we move the value / into RBX. We have to be careful about using little endian. So /flag is backwards. So this is FLAG, and so on. So we can build it up this way, or we can just write it directly to memory. And let's try the second one first. I suspect actually it might not work. So we can do this. Move RSP, move byte pointer RSP, /, let's see, and then move byte pointer RSP +1 F. Let's see what happens here. Huh. We got away with it so far. Okay. /F LAG. G 1 2 3 4, and then we need the null byte for this to be a valid string. Okay, of course, if you put a null byte there or put 0 there, right? Same thing. That's gonna end up with a null byte in our shellcode. So what do? Well, we can XOR. Can we XOR? No. We can XOR something we're not using, CL, and move CL into there. Boom. No null bytes. CL's a 0. That's the null terminator. RSP contains /flag RSP. The memory region pointed to by RSP contains now the word /flag, or will contain when this runs. Now we just need to point RDI at that. Of course, we can move RDI RSP. And we have a shellcode with no null bytes. Doesn't even have the word /flag in it. I mean, it does, broken up into these bytes. And if we strace this, we can see that it'll open the flag successfully. And this is on my local machine with my local test flag. And it'll print it out. All right, so let's SCP this. This is not how I would recommend using pwn.college. Do all your work on the instance itself, but I haven't set it up properly. So, sanity check. No zeros in the actual content. My bad. I neglected to put a pipe. Why did I just type reset after catting out binary data? The binary data sometimes is control characters for your terminal that'll set settings to be really weird. So after you do that, just get in the habit of running reset. It resets your terminal as much as it can to something normal. Anyways, we put in our shellcode. Here it is, and it works without any nulls. So, question in the Twitch. Hey, don't strings have to be null terminated? Yes, absolutely they do, and we null terminate this string. Look at it. It's right here. We write it /flag, and right afterwards we make a null byte, or we make a 0 value by XORing CL with itself, and then we write that into memory right after right after the /flag. Cool. All right. Another person said, so here's my hint. Now let's move on to level 12. Or not level 12, the 12 byte shellcode. So later levels are going to force you to squish your shellcode more and more and more. Here's my hint. Think back to embryo.io, right? Of course, I can do cat /flag. I mean, let's actually do this on my machine. Oh, okay. I can do cat /flag. Cool. If I am in / though, I can just do cat flag. That's 4 bytes. No /, right? So if I remove this and just put 1, 2, 3, 4, this is now shellcode that'll just do cat flag FLAG. Let me copy it over. If I run it from here, it's not going to work. Why? Because there is no file flag here. If I run it from here, though, from /, of course it will work because there is a file flag. Or if I make a symlink, you can make a symlink to a file you have no permissions to, no problem. Just a symlink in my home directory. Now I can run this. Okay, and it works. And of course, I can make the symlink named whatever I want. I can name it F. Of course, this won't work because there's no more symlink, but of course I can change my shellcode to just have F. And it works again because F was the file that got outputted out. So by using symlinks cleverly, of course, why am I doing this for my home directory? Because I can't make a symlink in slash called F. Because I can't create files here. So I do that in my home directory. By making that short file, I managed to decrease the size of this shellcode, right? That's going to be critical. The other thing is you can have almost any characters in those file names. So if there's already a string in memory somewhere, you could use that as a file name potentially. All right. That's going to be my hint on the 12 bytes. The other thing is think about how to compress shellcode as much as possible. We did it already a little bit, right? So, for example, this XOR RAX, RAX everywhere. XOR RAX is a 3-character instruction. And one of those characters is the hex 48, the ASCII letter H. This is the prefix for the instruction that says, hey, this is a 32-bit instruction. We saw another prefix, 66, that said that that's a 16-bit instruction, or that instruction will operate on 16-bit values, or 16-bit versions of the register. If we instead make this XOR EAX, well, let's do here, XOR ESI, right? Here we have a 3-byte instruction, 4831F6 for XOR RSI. Suddenly, 31F6 for XOR ESI. That's shorter, right? Shorter instruction. All right. Other questions? I think I can probably sustain another 17 minutes of... Oh, any tips for the bubble sort one? Absolutely. Can someone remind me, does the bubble sort one come before or after the 10-byte splitting your shellcode into 10 bytes? Let me take a look in a different terminal. It comes after, yeah. So my hint is that 10-byte jump, right? What if that 10-byte jump was a 4-byte jump? What would you have done? More jumps and nops. All right, is the answer for what you would have done if so there's a level where your shellcode is corrupted every 10 bytes, right? So then, of course, you have to deal with that. If you think about it, the bubble sort is almost equivalent. It is kind of a corruption of your shellcode every... let's say this. You can put in shellcode that's already sorted. And all you really lose control of is that last byte. The most significant character in little endian. So the last byte that is going to be what's checked to see the ordering of the code. So bubble sort is conceptually equivalent to the corrupted case. I'm going to blow my nose while people are thinking of more questions. Back. Man. This daycare sickness is not good. Is there a way to move an 8-byte value to the stack without using a register? An 8-byte value to the stack? No, I don't think so. Without even using RSP? All right. So, let's get back into IPython here. All right, here we go. You could have something like this. Let's say you wanted to push a 8-byte value to the stack without using a register. If you were okay with a 4-byte value, here's a 4-byte value. All right, big success. Hex 1. Let's make it a little more. Let's say A, B, C, D. All right. 8 lowercase h is push immediate, push 32-bit immediate. DCBA. Unfortunately, doesn't fly for 64-bit values. AMD was not so kind to us. Of course, you can build it up one letter at a time. And so on. Move byte pointer. Okay. Can you move keyword? Yes, you can even move keyword pointer. Oh, this I didn't realize. Haha. 41, 42, 43, 44, 45, 46, 47, 48. Nope. Doesn't like it. So you really just get the D word pointer. Okay, so you can do that, and then of course +4 here, and get the other 4 bytes. But so that actually, if your question was without writing a value to a register, this is by EX4722 on Twitch. EX, if you mean, is there a way to move an 8-byte value to the stack without overwriting a register? This is it. This doesn't write any registers. Of course, you have to remember endianness. I think this will be good. 4, 4, 4, 3, 4, 2, 4, 1, and then 4, 4, 7, 4, 6, 4, 5. Wait, I got confused. 8, 7, 6, 5. I think that will write A, B, C, D, E, F, G, H. All right. The question is, isn't there something like push absolute for x86 64? Not for 64-bit values, unfortunately. Push still deals. Push immediate still does 32-bit. I don't know why. Okay, the other questions. When are the next problem sets? It's a good question. The plan was that this baby shell would be due on the tomorrow, and then everything would launch tomorrow. Of course, baby jail would launch tomorrow. But unfortunately, over half the class hasn't solved baby shell level 1 yet. Whether that's because of the long weekend and everyone is out, or because embryo IO or embryo ASM is hard and people haven't made it through that. So the likely scenario is that we'll extend this module to Thursday, and then the next problem sets will launch on Thursday. But I haven't made that call yet. All right. What else? Other questions? Level 4. All right. Let's take a quick look at level 4, and then I will leave you with that. So we start up level 4. Here we are. We're in level 4. Let's just try to reuse our no null shellcode. Or let's just try to reuse our normal shellcode. Pipe that through. Boom. All right. Failed filter at byte 0. This challenge requires that your shellcode have no age bytes. What the hell is an age byte? An age byte, if you man ASCII, is hex 48. Hex 48, if you look up what that means in x86 land. So 48 is the REXW prefix. It says, hey, the operands of this instruction are 64 bits. This is the difference between move EAX and move RAX. And this is the brilliance of AMD to make AMD 64 actually a kind of non-dead on arrival architecture, right? Let me try to find the oh no, okay, here it is. Yeah. All right. AMD 64 wasn't the first jump in instruction size or in bit width of x86. It had bit widths of 8, 16, 32, but at each one they had the luxury of actually I don't know why AMD decided to do this what they did. So x86, when you are in, did x86 break binary compatibility? Anyways, as you saw earlier in the stream when we were looking at the 66 prefix that turned the 32-bit value register accesses into 16-bit register accesses. 32-bit is the default value. When they switched to 32-bit, it would have probably broken some assembly. But I guess there must have been solutions for that I'm not conceptualizing in my diseased state. But when we moved to 64-bit, that was done by having these prefixes. The prefix happens to be 48, and that is why we're not allowing you 48 into this into your shellcode. So you have to learn how to survive without the H byte. All right. So let's look at where our H bytes are. Let's look at our original shellcode first. Here's our normal, easy just open read write shellcode. Let's grab that for null bytes. Sorry, null bytes. H bytes. Okay, here it is, 48. Many instructions. All the instructions that deal with 64-bit stuff have this prefix. All right, that's a problem. One way to avoid this prefix that we already looked at is using the 32-bit values, right? And here in the no null shellcode, we had moved from XOR RSI RSI, which, where do we have another XOR RSI RSI? No, we have RDI. We don't, but which, like XOR RDI would have this 48, and we moved to XOR ESI ESI, which also, thanks to the way MD64 works, clears the rest of the RSI register, and we got rid of the H byte. So of course, we could probably do that for everybody. XOR XRAX. We could change it for the move, etc., etc. Let me do that real quick and then tell you why this doesn't work, and leave you from there. So a couple of things. This probably won't fly, but we no longer have restrictions on null bytes. So let's actually start from flag. So this is fine. This will zero out all of RSI. This is fine. It's fine. This, because EAX, the value in RAX returned from the syscall is small, is the file descriptor, so it's like 3, right, is fine. But this is not fine. Here we're moving the address of the stack, which is a 64-bit value, into ESI, which is a 32-bit register. The address of the stack, here's the address of the stack layout of cat. Okay. Here's cat. Here's where it's, or of the memory layout of cat, excuse me. Here's the stack. Cat stack, and any program stack on my machine is mapped somewhere in this very, very high memory range. And the 64-bit range of that is up to here. So when I move RAX, move ESI into ESP, or ESP into ESI rather, excuse me, I leave behind these values. And that's no longer a valid memory address. Right, let's do this. I'll show you that it passes the check, and then we'll go from there. With the exception, this will be hard to bypass, but I will leave you with that actually to figure out on your own. Okay, here we go. We changed all R to E except for this one. That's going to give us some trouble. Wait, yeah. All right, we have one thing, which is this flag. But hey, we learned how to do different things with the flag. No problem. Where's our in our null.s? We used this clever thing. Let's see if that has null bytes. We build the flag on the stack as F and use a symlink. All right, let's see. Will this have null bytes? It could. It doesn't. All right, we have a null byte free shellcode. Putting the flag in memory, into RSP, and actually if you forgot, we need to move RDI RSP. That has an H byte, so we need to do EDI ESP, which won't work. Remember. Boom. All right. No null bytes. Let's SCP this no H. Awesome. And let's run it. And it doesn't work. Of course. Why doesn't it work? Well, if we strace what's going on here, we try to open something absurd, right? Which is very unfortunate. And we try to read something absurd, and we try to write something absurd, right? This is supposed to be a memory address of where /flag lives. But instead, you can actually kind of see it. Can you kind of see it? No. How can we see it? We can see it in GDB. If I look in GDB, go start I. Here I am now in my shellcode, about to execute it. If I info proc map, this is where the stack is. FFDD000. Okay. Anyways, let's go with that. Okay. Let's start executing. Okay, this is me writing the flag. So let's see what is at RP. Our F value. Here is me moving ESP to EDI. Here's RDI, RSP, step. Here's RDI, and here's RSP. Okay, so RSP was, of course, GDB disables the address space layout randomization, but RSP was a very large value, and it got truncated when it was moved to EDI. So it doesn't fly. All right. So you will need to find a way to move that address, or you'll have to find a workaround without using an HByte. All right, there's a question. Does switching to 32-bit mode require us to have access to HBytes? You could switch to 32-bit mode completely, right? But probably that's much harder. I wouldn't deal with that. Someone asked, are you using vanilla GDB because you don't have other versions or you don't want to? I'm using vanilla GDB because it's the lowest common denominator among all of the different GDBs. So this should be hopefully approachable by everybody, regardless of whether to use PETA, Jeff, pwn.debug, pwn.gdb, etc. All right, cool. But for your case, I would actually recommend you choose one of the GDB distributions and set it up on pwn.college. You can go to /opt/pwn. Yeah, in /opt, there's either Jeff, which you can install using the resource in the README, or pwn.debug, which you can also use install using the resources in the debug. There might even be, no, there's not. Okay. Yeah. All right. There's a question. When you did the move byte pointer RSP 66, can't you have pushed 66 and popped into RDI? Or am I missing something? Play around with it. Oh, pop into RDI wouldn't work because I need to have the address of the path, not the value of the path in RDI. RDI, if you do man open, RDI is a pointer. It's a memory address. All right. Hold on. That's going to be the rest. That's going to be it for me for today. I'll hopefully be fully rested and ready to go tomorrow. Almost certainly we're having class online again, unless some miracle happens. But I have a feeling there's going to be one of those lingering problems. Anyways, we'll see. My daughter at least is showing better improvement than I am, which is good. Cool. Thank you for joining. Hopefully this had a lot of good information. As a recap, we went over level 1 and level 3 fully. So there's no excuse for anyone in the class not to get level 1 and level 3. And probably level 2 is very simple as well. I don't even remember what it is. So go tackle Baby Shell, and within a couple hours later tonight, I'll tell you what we've decided on extending the module to Thursday or not. All right. Thanks for joining, and see you tomorrow.